All right, here we are on the 5th. We'll do a couple more homework sets. This one, I'll put up a review on the 8th of this homework set. Because I don't want any, well, I want less confusion going into exam 1. So anyway, that's what we'll do. We'll have exam 1 on Friday.
So you're just gonna post and then we just do that?
Yeah, so you'll do the homework here. Hopefully you'll give it a try, and then Thursday night I'll do a little short video on the solutions to walk through them. Because you won't, like, if you turn it in on Friday, you won't, and you had confusion with it, that's not really gonna be, that's not gonna be great. Maybe we might actually do some of this in class on the 7th, so. Anyway, I don't want to build confusion into Friday. Follow me?
Yeah.
If I just gave you this homework set, normally you would turn it in on Friday when you come into class, but if you had a bunch of questions, you wouldn't get them answered, so. I don't want that. It's chapter 4, I mean, it's not too bad, but you'll confuse it with chapter 1, 2, and 3, because it forces a shift, right? We move into equilibrium, so. All right, let's do free body diagrams. That's what you were doing. So this was the first one, which didn't even give you all the information to actually solve it. So that's good. All you could do was a free body diagram. 1 and 2, right? You did 1, 2, and prep 9 was the plan. All right. So given a beam of some kind, a cable support, and a pin, you're supposed to draw the free body diagram. So as these get more complicated, we have to think about what we're going to draw the free body diagram of. Obviously, we're drawing it of the beam. So when we do that, we want all the information on the drawing and supports removed and the reactions put in. So don't forget that the reaction list is like, I don't know, 5 or 6 pages back. You probably don't have them memorized yet, but they're really not that complicated. Here's the reaction list. A rope, a cable, a chain, a wire, a string, any of that kind of thing is going to get 1 reaction. And a pin, same as the knife edge, is going to get 2. X and Y. Okay. So this one, you didn't have to draw both. You could have went straight to the free body diagram. I'm okay with that. Same thing on the exam. Same thing on homework problems. You can go straight to the free body diagram. You don't need to give me 2 diagrams. You don't need it. I did 2 just to talk through it. So our goal is to draw this thing and create what's called a free body diagram. This thing is going to be hovering in space. The reactions are gone. I'll make them red, or the supports are gone and the reactions are put in. So the reactions are the vectors that replace the supports. This is a cable. All right. So it's going to get 1. And the way I do it is I put them in first and then I think about directions. And then a pin gets how many? 2. They can be above, they can be below. You know, this could have went up, this could have went left. That doesn't matter. Yeah, does not matter. We want to label them. So this should be BX. This should be BY. My red pin is just done. And this one would be what? AY. Yeah. All right, so then you want to think about the external forces. They have to all be on there. So these things have to be complete. We want to work the problem from our free body diagram. Our distances need to be on. I don't think they gave us a distance. Oh, they gave us overall L. Right? Now we think about directions. So super important that you get your directions in and you guess at it. And if you don't know, you just put them in. Because when we solve the problems, the mathematics will tell us whether we're right or wrong, okay? So we know which way the cable goes. It can only hold in tension. Okay, so if you're drawing the free body diagram and struggling with directions, just think about you are this beam and what do you feel from the cable? You feel a force going up. It's gotta, right? That's what a cable does. It cannot, a cable or a chain cannot push on something. It's gonna always pull away. If you drew the free body diagram of this earth up here, then it would point down. That's what the cable would do. So we can draw a free body diagram of different things. We're obviously doing the beam, right? And then what over here, we think about, all right, which way would these go to put this thing in equilibrium? Because statics it means things are not moving.
So up and then to the right.
Yeah, it's got to go up. And do we know this one? The X? Well, we do know what it is. 0. There is no X force out here. There's no other X force. So we do put it in, we do give it a direction, but we could note that it's equal to 0. If there's no other X force out there, it's got to be equal to 0. We cannot have leftover forces. So that's kind of what the rest of this chapter is about, is equilibrium, which means all the forces in the X are equal to 0. And all the forces in the Y, when you add them up, are equal to 0. And all the moments are equal to 0. So there's these 3 cases, but we'll talk about that when we do number 9. Questions on this one? That makes sense? Kevin says, yep, got it.
Is the pins like always going like basically away and then up?
Not always. No, it can go in and down. Depends on what the forces are in the system. It's always X and Y, and the pin is always 2.
Yeah.
That's the part right now. That's all you need to know. Like free body diagrams, if you got a pin that you're removing, you put 2 supports in. The supports, these vectors, BX, BY, and AY, they're called reactions. And this is fairly important. They're vectors and they're forces, but they're different than the external loads on the system. The external loads on the system are given, right? We're going to know them. The reactions are unknown, and we put them in for supports. All right, let's look at this one. Number 2. We have this L-shaped, upside down L-shaped system. It's got a pin down at the bottom. So how many does that get? 2. So you just put them in and label them. What are they labeled? Yeah, AX and AY. And that's just so we all have the same variables. Like when we're talking, like we all understand like, oh, AX, that's here. AY, that's here. And then what's this, like a cable? Yeah, it gets 1. It is on its line of action. So it stays along this line of action. Did they give us an angle for that? Unknown theta. And then which way does it go? Yep. It always pulls on something. Cables cannot push. They always pull. Is there any other external loads? Yep. We need this one. This is the free body diagram. They gave us a distance of 6 feet. Any other distance? Yeah, 13 top to bottom. So I'll put it over here. All that needs to be on there. If they label points, we want to label the same points. All right, what do you think? If this thing's going to be, yeah.
What would you label the cable as? Would you label it BY, X?
Yeah, we want to label that unknown, and you can, I mean, It would not be by or bx because it's not in the x or y, right? I would label it C for cable. But you can label it however you want, just don't label it X and Y, unless it is in the X and it is in the Y. Right? That's what that notation means. That's horizontal, that's vertical. Good question. Well, we want to label it, we have to, because we're going to want to find that force at some point. You have another question? You're good. All right, what about these directions? If we're thinking about this thing, now it's just in space, right? It no longer has a cable, it no longer has a pin. How is it gonna just stay here in space and not move? These directions are gonna keep it in its position. Which way does this have to go? Up. Why? Yeah, because we have down force and we have to fight that. It's got to go up. What about X? It's got to go to the right because there's a component of the cable that's going left. Okay. Again, these are going to get complicated enough that you can't figure them out, but sometimes you can. I'm 100% sure that the AY goes up. It's the only up force and it's got to counter the 10 in the cable coming down. And I'm 100% sure AX is to the right because there is a left component to the cable. But these are going to get so complicated. I mean, if we added another force to the right, then I wouldn't know which way AX goes. You know, without doing the math, I wouldn't know. So even if you don't know, you want to put in a direction, make that assumption. Then when you do the math, it'll correct us if we're wrong. We don't make a mistake. I think that's it. That's all of the free body diagrams. Sometimes, just gonna highlight this. Sometimes you're gonna need points like that point. So maybe this is point D. Right? So sometimes you'll need those points to work the problem. So it's not wrong to like extend lines of action and have more points outside of the object. That's perfectly fine for your free body diagram. There will be a free body diagram on the exam on Friday. There you go. That'll be just like bonus, throw you a bone problem. Just don't muck it up. Get everything on it. Get everything labeled, all vectors labeled, all distances on it. It's as if you're going to work the problem from the free body diagram. You got to have all the information on it. Questions on number 2? It's good. Hi, Jorge.
Hello,
I haven't seen you in forever, man.
3 weeks.
I'm like, stranger just walked into the class, you guys.
Sorry, I'm late. I woke up late.
Oh, it's fine, man. Whatever you missed, you can go back and watch the recording if you think it was fun.
I've been doing it, but because I work weekends.
Yeah, well, and you haven't been here, so you better be doing it, and you're doing fine, so. All right, let's talk about number 9, and we should talk about equilibrium first. Because the only way to solve number 9 is by applying the equations of equilibrium. So here's the problem. It says calculate the force in cable AB. That's this cable. And the angle theta. So 2 unknowns for the support system shown. So I've started the free body diagram. But let's talk about equilibrium. So equilibrium is this concept of things at rest, right? So if you look around the room, pretty much everything is in equilibrium except for us. I'm moving, talking, right? But my camera, the book, you know, all the stuff on the desks themselves, the building around us, that's a good thing. It's in equilibrium, right? So the concept of this is that all the forces acting on these things are equal to 0. In other words, all the downforce on this desk, and there's a bunch of downforce, right? You could weigh all of these objects the computer, the speakers, everything. Add up that weight. The table itself has weight, right? And all of that is going down. So there must be an equal forces going up. And I think these tables have like 4 little round legs on them, right? So if you added all this up, there would be a different weight on all 4 legs, right? It's not evenly distributed. Like there's a load here, there's a load here, there's a load here, but there seems to be like less over here, more over here, right? But nothing's moving. So those up forces must equal these down forces. Does that make sense? There's no X force unless I do this. Now, oh, it's not move. Now there's an X force. So the structure must be resisting that X force, right? So all the forces in the X are equal to 0. All the forces in the Y are equal to 0. Now, I'm going to push on this again, and you do see it move, right? I'll push on a little harder. It's not move. So the other thing is, with me pushing on it here, where are the supports for this table? Way down there. It's the friction, basically, between the concrete and the table, right? So this X force actually is also trying to rotate this thing. And there must be some resistance to that rotation. Agreed? That's called the moment. We know that. So that must be equal to 0 also. So X equal to 0, Y equal to 0, and the moment has to be equal to 0 for equilibrium to be true. We write that with equations that summation forces in the X equal 0. Meaning add up all the forces, it's got to be equal to 0. Add up all the Y forces, got to be equal to 0. Add up all the moments, they've got to be equal to 0. This moment is the moment anywhere on the system. In other words, if I add the moments right here of all of this, it would equal 0. If I calculate the moments at this spot, remember, a moment is very specific to a location. Of this whole table, it's equal to 0, right? When I was with Hewitt designing their maintenance trucks, we had these pretty big trucks, right? I remember then a big flatbed. We put all these tanks on here and these pumps, more tanks. I could not exceed legal haul on the highway. And that means a certain amount of load here and a certain amount of load here. It had to be within the regulations. So I had to calculate all of these moments of literally every weight on this truck about this spot or this spot to determine what that weight distribution was. Because it's also an equilibrium, right? It's not flying anywhere. But I can only have so much load and so much load on the front axles and the back axles. All right. So that's the concept. The way we apply it is we just apply it. And you'll hear me say, apply the, if you don't know what to do, look at this problem and you're like, oh my God, I don't know what to do. You determine it's an equilibrium problem, right? If you determine that, just apply the equations, write them out. So that's what I'm going to do to solve this. First, I'm going to draw the free body diagram. This is a cable, so we know it does this. I'm doing the free body diagram of point B. And I'm going to put it in equilibrium. So I'll call this, I'm going to actually call this AB because there was point A and point B. But that's my cable. How much was the weight down? 200 pounds. Goes down, right? And we have 100 pounds over. Yeah. And then theta is also where? It's also right there, isn't it? Theta here, theta there. Kind of that opposite angles of a straight line, right? Okay. This is a little mathematical because we have to write these equations and we're going to have unknowns in. Now, it's a concurrent system, meaning all the forces go through point B, correct? So now we gotta think back to, concurrent systems, was there any moment with a concurrent system about point B? Is there any rotational effect? Do all the forces go through point B? Yep. So it's like taking your finger and pushing on the door hinge, nothing's gonna happen, right? There's no moment. So in a concurrent system, the moment equation drops out. We don't need to do it. There is no moment. You would go force times 0, and force times 0, and force times 0 to calculate the moments and be a big 0. All right, so that leaves us two equations, Fx and Fy. So I'm gonna write some forces in the X, and I'm just gonna literally pick them out and put them in. All right, what are the forces in the X? Yeah, do the easy one first. Is it plus or minus?
Plus.
Plus. And we get the sign of a force by its direction, and it's going positive to the right. So plus 100 pounds. Are there any other forces in the X? Yeah,
Yeah,
which one?
maybe.
ABX. That one. Correct? The X component of AB. So I'm going to write it. So that's adjacent to the angle theta, correct? Everyone agree with that? Yeah, so I'm going to write cosine angle theta equals ABX over AB. It's a little mathematical. It's just a regular cosine, right? Without knowing anything. But I want ABX in this equation, so I'm gonna solve for ABX. That make sense? All right, what is that? ABX equals what? Cosine theta times AB, correct? Yeah. So I'm gonna write that in. Is it positive or negative for this equation? Negative. Negative cosine theta times AB. That's got to be equal to 0. But how many variables are in this? How many unknowns? 2 of them. So we can't solve that. That's 2 unknowns, 1 equation. All right, let's write the next equation. What are the forces in the Y? Negative 200 pounds. And unknown ABY. So right there, ABY. And again, if I write that equation, it's going to be sine theta equals ABY over AB. ABY, which is what I want in this equation, is going to be AB times sine theta. Is it positive or negative? Yeah, AB has up effect, and the up is positive, plus. Set it equal to 0. Again, this is a lot of your problems are going to get in equilibrium. You won't have 2 unknowns. So this one's a little unique in that there's 2 unknowns. If you end up with 2 unknowns like this, you need 2 equations. You can't just have 1 equation. You'll be stuck. But now we have 2 equations and 2 unknowns, and the unknowns are the same. AB and AB, theta and theta. Anyone remember how to solve 2 equations, 2 unknowns? We've done it before in this class.
Well, you just like switch it out so that like, I don't even know how to. explain
That's
it.
right, you switch it out, but there's another word for that, substitution,
Oh,
right? You solve for one, substitute it into the other one. So either one, any one you can solve. Solving for the angle is a little more complicated, let me tell you. So I would solve for AB. Pick one equation and solve for AB. So these set up with some notation to start, right? But that's just to keep things straight. The equation is really that. This equal to 0, this equal to 0. These are not variables, that's just what they are, what the equation is, right? So these kind of just go away. And you end up with this and this. I'll take this one and solve for AB. You do that too, and then we'll see what we get. So AB, I'm gonna first move the 200 over. Right, that's basic algebra rule. And then how do I get AB by itself? Yep. Divide by the sine theta on this side, it crosses out. So now I know what AB is equal to. And we take that and we go right up there with it. We could have solved for theta and plugged that in. Either way. If this math looks complicated, it does to me. Is there another way? This will work. We can keep going, but let's go back up and just conceptually look at this thing. Yeah, If-
X force cosine, Y force sine,
mm-hmm.
do like opposite over adjacent, to go.
We could, but I'm looking for something else here. I'm fishing for something. Look at this.
Okay.
If this is in equilibrium, in other words, if all the X forces are equal to 0 and all the Y forces are equal to 0, can anyone conceptually see what's got to happen here?
Yeah,
Alright.
I was thinking that, the force X 100 to the right, which is positive, has to be the same as the force on the other side because it's equilibrium.
Absolutely. So let's write this again. Some forces in the X plus 100 minus ABX equals 0. Yeah? That looks a heck of a lot easier than where we were heading with simultaneous equations. But that meant we had to draw a free body diagram. We really had to think about like, wait, X and X have to be equal. So ABX is equal to what? 100 pounds,
Actually,
right?
minus.
Yeah, no, it's got to go to the left. This helps us with that. And I put it in minus, right? But then I move it over here, it becomes positive. So this is, so here's the deal. The 100 pounds comes out positive. That means your ABX guess at its direction, your assumption at its direction is correct. Because ABX does point left, right? Everyone agree with that? It's got to. Huh? Oh, it's definitely straight. If this is straight, then this is straight, right? These two are equal and opposite. They have to be. They're the only two X forces, right? And there's only two Y forces, correct? Yeah, this up and this down. So ABY has to equal 200. And it has to go up because this one comes down. Yeah? Everyone good with this? New concept here? So you want to draw your free body diagrams and you want to think about it. Now, if there's two unknowns in a direction, you cannot just like guess, oh, I think they're this, right? there is one in each direction, so this works. If there was more than one in each direction, right? Unknown, you can't do that, you're gonna have to do the math. But this works. This tells me that the x component of AB is 100 and the y component of AB is 200. So how can we get AB? Yep. Pythagorean theorem. Do it. You already did it. 1, 2, 3, is that right? Is there a 1, 2, 3 triangle? A lot of things like that. No. So I get AB equal to what? Anybody else get a number? Yeah. 606.7 pounds. We would round that for the answer. And then they wanted to know theta. So it's acting here. That's the angle I want. It's going to be opposite over adjacent, y over x. So 200, 100 by inverse tangent. 63.43. 63.43 degrees. We would round this to 61 and I would get rid of that. So the kind of the big picture thing there is draw your free body diagram, take a look and see if, because everything we look at kind of from chapter 4 on, we look at in the x direction and we look at it in the y direction and we look at it in the moment. Those are how we're going to look at these problems. Forces are going to be like all over the place, but I'm going to think about x effect and y effect. Okay. Give yourself like a red star on that problem right there. Because that's part of your homework. You will turn that in for 10 points. And the other 2. So free body diagram and number 9. Turn in, I'll take them. Pass them to your right or something. Make a pot.
How long you down? I did the wrong.
Nice job, Nick.
Oh,
Turn them in. You just say I did the wrong one, so now it's gonna give you the point.
Hey, so when I sent you the message, I guess when I took the picture, I didn't,
Cam scanner, it's easy to not.
because you can check it off, it'll
Yeah.
just send one, so I
Yeah.
could have verified it, but
That's all right.
I have it right here.
Thanks. Good job on the quiz, everybody. Are there any questions on the quiz before I head off into chapter 4 world? No? All right, so there'll be kind of a problem like that on Friday also. That makes you think in the X and Y, right? Instead of like vectors off at angles, I want to know what X effect and Y effect is of a system. That's how we do the analysis.
That's gonna go on Friday for the press.
There'll be one of those on Friday. Yep. Very similar to that problem we just worked on. I don't know about concurrent system with all the unknowns. I'll probably give you knowns and just have you determine. So the other thing is I can just ask, is it in equilibrium? Right? And that just means you got to apply the 3 equations. Like you got to check X, you got to check Y, and you got to check the moment. All right, let's do, and I'm just going to make these up. So give ourselves a beam. We'll make it 20 feet long We have a lot of beams in our world, 20 feet long. Gonna put a roller at this end, a pin at this end. Gonna put a force on it of 1 kip. How much is a kip? Yep, 1,000 pounds. And then I'll put another force on here of 0.2 kip. And we'll make it 6 feet. Oh, that's not very balanced out. 6, what do we need? We need
Break it a little bit down.
7 feet and 7.
Like that.
Yep. 14, 20 feet. Yeah, I got it. 7 feet, 7 feet, and 6 feet. 2 kip, 0.2 kip, 0.2. That's important. And the question would be, find the reactions.
You want location too?
Huh?
Do you want location too?
No, because I didn't say find the resultant. I said find the reactions. What are the reactions again?
The supports removed.
The support's removed and the reactions are put in. So there'll be how many reactions at B? It's a roller, 1. And how many reactions at the pin? 2. You can go straight to free body diagram if you want.
Say 20. Oh, 20.
20. Label them. All right, help me with my directions. So at BY, we think it goes up. Okay. Rollers can't hold down, right? But that doesn't mean the problem couldn't be messed up load wise. Like maybe we would calculate that, you know, BY has to hold down and that would tell us, oh, rollers can't hold down. So that support's bad. Like we got to figure something else out. So it is an assumption that we put in, hey, BY's got to be up because that's a roller. It can't hold down. But if this was to come up negative, that would mean, oh, we have a problem here. Like a negative means our assumption of direction is incorrect. So if I calculate BY to be negative, that means this is wrong. I guessed incorrectly. Okay. So hopefully that won't happen. I think I did my loads correct, but we'll see. Which way on AY? I would think up, but maybe down because there's this 1K going down, there's just 0.2K going up, right? But 1K is further away, so it's hard to tell. I don't know for sure which way it goes. So you just make an assumption and you say, okay, I'm gonna guess up. You can guess down if you want, and you'll see what happens with the math. And then what do you think about AX? Yeah, it's gonna be equal to 0, but I put a vector in and then I just label it 0. There's no X force on the system. If I take my arms off of this table, those feet, they do have some holding capability. It's called friction, right? If there was an X force and it wasn't too much, this table would stay put. But there is no X force. No wind blowing. There's no seismic activity going on, right? There's X is equal to 0. All right, so free body diagram is critical. And then we apply the equations. Some forces in the, if you don't know what to do, apply the equations. So I'm going to do it. Some forces in the X is equal to 0 is equal to AX. Right? So I actually wrote it. There's one force, it's AX, and it's equal to 0. The second equation. What are all the forces in the Y? One kip down. I heard that first. So when I do it, I work from one end to the other so I don't miss anything. Like you'll get some pretty complicated things. You got to figure out a way where you're not going to miss a force. So if I was doing this, I'd start here, 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 here. But I heard one kip, so I wrote it. Give me another one. 0.2 down, right? Or it's up, yeah, 0.2K is up. What else? BY, which way? Plus BY. What else? Plus AY. Any other Y forces? Nope. Set it equal to 0. How many unknown? 2. One equation, 2 unknown, can't solve it. There is another equation. It's moments. Often you'll need all 3 equations to solve these things. Now is when we have to choose, like, where do you want to do the moment? It's up to us. I would do it where it drops out as many forces as possible. In other words, wherever you do the moment, if there's forces there, they're not going to contribute to the moment at that location, right? If I do it here, how many forces drop out of the moment equation? 2. Which 2? AX, AY. They both, neither one of these create moment about here. Agreed? They go right through it. So their force times distance is 0. What about here? How many drop out? BY? Yeah. Hey, wait a second. What about AX? Doesn't it also drop out? Yeah, it does. But it's also 0, so I probably don't need to worry about it, right? But think about that when you choose your spot, like any force that goes through that spot drops out of the moment equation. All right, this is the obvious spot. If you do it here, that's fine. Only one drops out and you have a few more moments to do. Actually, this drops out too, so any spot's a good spot. Let's do A. Moment at A. Again, you got to pick a spot, right? And the moment at that spot has to be equal to 0 for equilibrium to be true. And all of our problems are equilibrium problems. This is statics. Things are static. All right, what are all the moments about A? Force times distance, right? Which one do you want to do first? 0.2. 0.2 kips times 6 feet. Yeah, 6 feet. So we're doing moments at A. You have to remember where you're doing it, where you chose. Moment at A, and then what kind of rotation does point two make about point A?
Counterclockwise.
Negative.
It is.
Or clockwise.
Clockwise, which is negative. So you gotta shift your brain like, oh, I'm doing moments now. I gotta think rotation. What else creates moment about A? You need to include them all. Everything that creates moment. Yep, 1K does. 1K times
13 feet.
13 feet. And what kind of rotation?
Negative. Positive.
About point A. Positive. Plus. You have to remember where you are positioned. We are positioned at A. What else creates moment? BY does. And BY times 20, and its rotation. We drew it up, correct? Yeah. So here's where our assumption of the force going up makes that a negative. It's good. Just stick with it. Whatever you decide on directions, you just stay with it. All of that is equal to 0. How many unknowns? 1. Solve for BY. So keep the sign straight. This is a negative, so we're going to take BY, move it to the other side, becomes positive. Then it's going to be this negative, this positive, divided by 20. So don't forget your algebra. This negative statement would move over and become positive. And then we need BY by itself, so we divide this side by 20. All right, let's see what we get. I got a number? How big do we think it should be? We got 1K here, got 0.2 going up. It's not carrying all the load. I think it should be less than a K. I get 0.59. Anybody else get 0.59? No? I'll do it again. Yep, 0.59 again. Uh-oh.
Yeah, let me see how you play the thing back.
All right, so what's this number right here? 0.2 times 6. So I'll write out long form. This is minus 1.2. That's what this is. Right? This is 13. And that is equal to BY times 20. So that's the long form.
Then we divide there,
Yeah, so then we gotta add these two together. Yeah,
then divide it by 20.
uh-huh. So now we have 11.8 equals BY 20. So 11.8 divided by 20. BY equals 0.5 now. What are the starting units? Kips. Yeah, so it's definitely kips. And did it come out positive? That's super important. It did. It came out positive. And the positive means that the assumption of the direction of By is correct. Goes up. That means our roller's good, because the roller can support the way we chose, right? A roller can push up. A roller's no good, cannot push down. Right? No hold down in a roller. Do we use rollers in the real world? Absolutely. Every structure like that has any expansion and contraction has a roller connection. Like you drive across the Fremont Bridge, that giant bridge, it has huge expansion joints. Those expansion joints, they're giant. They're like 4 feet on the Fremont, right? It's a bridge that looks like this. And then underneath this area, it's not connected. Like the bridge is literally sitting on this surface. So maybe we got a pin over here, and we got a pin over here. But here, that's a free end. Now, there is a lot of friction. So there is some X support, but not much compared to the size of the bridge, the weight of the bridge, and the load the bridge carries. This friction capability is like 0. It's not really gonna do much, right? But what it allows is it allows this, and this is probably fixed right here. So it allows it to slide and move. When it heats up, it expands. We have to have it expand. When it cools down, it contracts. It's got to be able to move. So that's what we're calling a roller, right? It's really an expansion joint of some kind. Good. Now what? So we got By. Yeah, so now we can take it and where can I draw my arrow? Plug it in. Oops, right there. That went right by it. Right? We can plug it in. We can take it back to the Y equation and plug it in. So we know that By is 0.59. And you would want all the precision. I'm getting like, oh, I guess you can see it very well, but I'm getting 0, 0, 0 after that, like it's precise, 0.59. So that'll give us AY. Now, AY's here, so just keep your algebra straight. That means you gotta leave AY here. By would move over, become negative. 0.2 moves over, becomes negative. 1 moves over and is positive, right? So just don't forget your algebra. I get for AY, what'd you get? 0.21K. And I get positive. Which means, what's the positive mean? AY, the direction of AY is correct. That it's up. So this is the one we weren't exactly sure of whether this was going to hold down or push up. It's definitely pushing up at 0.21K. So there they are, reaction 1, reaction 2, and reaction 3. Statics gives us this information. Strength of materials could then design the pin. Because I know exactly what's going on at the pin at A now, right? I know there's no X force and there's 0.21K in the Y. 0.21K, 210 pounds. I need a pin that will carry that load. Questions? All right, let's take a short break and we'll do another one. A lot of practice is needed with these. Make it a little more complicated. And I'll look at your homework and try and get one just like it. What is your homework? A little bit late, huh, Sean? You all missed a little bit. That's all right. You'll catch up. Y equation. And that's gotta be equal to 0. So AY is positive, stays here. This all moves to the other side. $26.04. That's actually 05. Was up. Comes out positive, means our direction's good. Anybody else get 27 or 26.047? Yeah.
Yeah.
Sweet. We're killing it. Engineering firm is rolling. We can build this out for, 150 an hour kind of thing. All right, now the tough one. We need this moment. There's 3 reactions for a fixed. 1, 2, 3. Write it out. Just write it out. That's what I heard. Some moment at A. What are all the moments at A? 170 times 40. Rotation. Be counterclockwise positive. 200 times 40. Rotation. Negative. Any other moments? Yeah, so the X component creates moment, the Y component would be right here. Right, of the 150. The Y component would not create moment, it goes right through the point. So this X force, it creates moment about A. So we can just use the X force, 147.
No, positive one.
Rotated about, yep. And that X force creates what kind of moment? Sorry, I lost my 1 there. Yeah, it's going this way also. So it's negative. There's no unknowns. Wait, we forgot one. We include this because we're doing moments here. We include MA. And I put it in counterclockwise plus MA equal 0. So if you don't include MA, you won't have an unknown. Like you won't have anything to solve. There's a bunch of numbers, right? Number, number, number. So we include our moment and our direction that we assume. And I assumed this direction, which is positive. That means that all of this switch signs moves to the other side and I just calculate.
Although it doesn't have one.
Whoa. 7108, man, that's dyslexia. 7108.
This is architectural.
And what are the units of moment at A? Foot pounds. And did it come out positive?
Yeah.
Yeah, so that confirms our direction choice for the moment of A. One reaction, two reaction, three reactions for a fixed support. Cool? It's kind of cool. 710885. Is that what we see? Is that what you got? Yeah?
Yep.
So then, just for fun. Next term, strength of materials, we will put it in this equation. This is the bending stress equation, right? Guess what M stands for? Moment. 7108.85. What were the units? Foot pounds. So to calculate the bending stress, we need the maximum moment. And that is the only moment, and it clearly is the maximum moment on the whole dang system, right? So, what are you doing?
What is the thing that, it's
Shear?
like
Shear force?
this-
That's shear.
No, the section, something, the.
Section modulus,
With the
cross section.
cross section.
That's what you're talking about. Yeah. Not yet. See? See, okay, so here's the cross section of our telephone pole, right? So when you cut your telephone pole, like you cut your water bottle, it's a circle. Yeah, this is not statics, this is for fun. Sorry, this is my weirdness. That is fun. How big do you think a telephone pole is? Let's keep it easy. 1.5 would be 18.
About,
I don't think they're 30. Jeez, that thing's huge.
about 18 inches.
Okay, we'll go 18 inches. 1.5 feet diameter, right? So C is the distance. That's called the neutral axis. That's the geometric center. C is the distance from the neutral axis to the outermost fiber. C.
So it would be a radius.
It's the radius, yeah.
0.9. I mean, no, it would be
0.75 feet.
Yes.
And I'm doing it in feet because I got feet there, right? I really should be doing it in inches because we're gonna get the inertia in inches. I is area moment of inertia. Since the book is statics and strength of materials, there's I calculations in the back.
We're gonna be using the same clip.
Absolutely.
Great.
Yeah, no kidding. So check it out. Here's I. What is it? Pi d to the fourth, and d is the diameter. Pi d to the fourth over 64. That's how we calculate the inertia. All right, we can do this. Pi d to the fourth over 64. What's my d? 1.5? 1. Got something against strength of materials. I know I'm not supposed to be doing it yet, but I don't care.
The sign.
That's right. 1.5 to the fourth over 64. Somebody crunch that for me.
I get 1.03. Or you want the whole number?
I don't get that.
You get that?
I didn't.
So-
Anybody else crunch it?
Oh, sorry.
Come on, team. I'll do it again too. I could have screwed it. Up. Yeah, I get 0.285. I equals 0.285 feet to the 4th. What a weird unit. Super weird unit. This goes here. So now I can calculate my bending stress. Whoa. Uh-oh.
240.
Getting to the punchline. I get 21,454. Anyone else get that? Anyone else doing it? It's okay if you're not.
I thought it was, the internship was 245.
Is it 2485?
Thanks.
Oh, it is 2485. That's what I used to get this. So this would be PSF, pounds per square foot. We need it in pounds per square inch, so we have to divide by 144, and that's 148 then for bending stress, 148.99 PSI. Cool? Doug Fir, limit, bending stress, Doug Fir's limit in bending stress, 900. That's what we compare that to. What do you think? What kind of factor of safety is that?
I don't know.
It's good. That's a good factor of safety, right?
Yeah.
So what is the factor of safety? I take 900 and divide it by the 148. That's a 6.04. It's a 6 factor of safety. That is a good telephone pole design. Boom, we're done. All right, give me your extra credit problem. I'll take that. Do all 3 homework assignments, even though we did the one in class. Do it. Turn it in. You'll get points for it. So. Nice job, people.